Hello everyone, this is Maushami. Now this is a very common topic that you have been encountering from the beginning, from the time when you have started studying physics. But to tell you the truth, people often think that this topic is not that important and not many questions come on this. But in fact, to note is that both JEE mains as well as JEE advanced, they have minimum one question on this topic. So let us look at some sorted out problems on this topic. The first one, sometimes it is convenient to construct a system of units so that all quantities can be expressed in terms of only one physical quantity. In one such system, the dimensions of different quantities are given in terms of a quantity x as follows: position as x to the power alpha, speed as x to the power beta, acceleration as x to the power p, linear momentum as x to the power q, force as x to the power r. Then, which of the following relations will hold good? Let us first look at the quantities and try to recall the relations between these physical quantities so that we can derive the required condition or conditions. So the first thing that we have here is position. The dimension of position is represented as x to the power alpha. Now we have speed next, indicated by x to the power beta. Now try to recall the relation between speed and position. So speed is nothing but position per unit time. So what we see here is position by speed will have the dimensions of time. So this is the keynote that we have here. We may write, combining the relations that we have, we may write the dimension of position, that is x to the power alpha, by the dimension of speed, that is x to the power beta, as equal to the dimension of time. Or we may write that the dimension of time is nothing but dimension of x to the power alpha minus beta. Let me write this equation as equation number 1. Now, looking at the next few quantities that we have in hand, we have acceleration given as x to the power p. Now note, acceleration is nothing but change in velocity to the time taken. Velocity and speed are equal in magnitudes. So from here also we can get the dimensions of time. So as we can see, we may write acceleration, which is velocity per unit time, and velocity and speed may be regarded as equivalent as far as their magnitudes are concerned. So speed is nothing but position by time. So let's equate these and try to get the relation between them. We may write acceleration by speed this is nothing but x to the power p by this was x to the power beta, or we may write it as x to the power p minus beta. Now to try to understand the dimensions of this particular ratio. So acceleration is nothing but velocity by time and speed is nothing but velocity. So this is having the dimensions of 1 by time, or we may see that from here we may write that the dimensions of time are basically x to the power beta minus p. just the reverse of this, as this is bearing the dimensions of 1 by time. So let me take this relation as equation number 2. Now time for the last one, the last relation that we have. We have linear momentum, the dimension of it as x to the power q. Try to recall, linear momentum is nothing but mass times the velocity, and we have force, the dimension of force expressed as x to the power r, and force is nothing but mass times the acceleration. So if you try to understand how we can express them in similar quantities of time, this is mass times the velocity and this is mass times the acceleration, and we already know that speed by acceleration has the dimensions of time. So similar keynote will be applied in this case as well. So we may write here that linear momentum the dimensions of it to the force mass times velocity, mass times acceleration, which is velocity by time. So this is bearing the dimensions of time, and we see that dimensionally we may write it as x to the power q by x to the power r, which is x to the power q minus r. So this is also bearing the dimensions of time. So this is our third relation. Now considering the three equations that we have in hand, we can very well get a relation between all of the quantities. Just have a look at this. We have x to the power alpha minus beta as equal to x to the power beta minus p, and this is again equal to x to the power q minus r. So have a look at this. It is the same physical quantity, so we may write alpha minus beta as equal to beta minus p, or we may also write beta minus p as equal to q minus r. Now keeping an eye on the options that we have in hand, let's see which of the options will hold good here. So for the first one, if we try to obtain the value of beta as per the first relation, we shall see that alpha plus p is equal to 2 beta. So we see that option A stands correct. Okay. So now let me analyze the second relation as well. So if you take a note on this, we have an expression of beta here. So if we try to find out beta from the next equation, it will be equal to p plus q minus r. So we see that the second relation also holds good. Now keeping an eye on the other relations, if p plus q minus r is equal to beta, then the fourth option can never be true. And keeping an eye on the second relation, let's try to see if this also holds good or not. For that, what we need to do is that we need to find out alpha. Now we have already got that the first two relations are correct. So let us try and use the third relation and try to see that what the value of alpha should come out as. Now if from the first relation, if we try to find out alpha, we can see that alpha will be equal to 2 beta minus p. So substituting the value of beta from the second relation, we see that 2 beta will be equal to 2p plus 2q minus 2r minus another p. So we see that alpha becomes equal to p plus 2q minus 2r. So obviously the third relation is also not true. So this was a very wonderful problem. Now let's have a look at the second one, which bears one of the instruments of measurements of distance. a very important one. This is the case of a vernier calipers. Now, we have been using meter scale regularly. For a meter scale, the smallest measure that we can take accurately is equal to 1 millimeter. Now, let us look at the case of a vernier calipers. The smallest division on the main scale of a vernier calipers is 0.1 centimeters. 10 divisions of the vernier scale correspond to 9 divisions of the main scale. The figure below on the left shows the reading of this calipers with no gap between its two jaws. The figure on the right shows the reading with a solid sphere held between the jaws. The correct diameter of the sphere is. So, beautiful problem involving a lot of concepts. Just have a look at the diagrams that we have in hand. So, as you can see, this is the main scale and this is the vernier scale. Now, the difference between the two scales is that the 9 divisions, there are 10 divisions in the vernier scale, and these 10 divisions basically they correspond to 9 divisions of the main scale. Now, the smallest division on the main scale of a vernier calipers is 0.1 centimeter. So, let us first use this data to find out the least count of the vernier calipers. The relation for this is that least count is given by the ratio of the smallest division on the main scale of a vernier calipers, that is smallest division or the minimum division of main scale to the total number of divisions of vernier scale. Now, the smallest division of the main scale is equal to 0.1 centimeters and the total number of divisions of the vernier scale is equal to 10. So, this gives us the least count as equal to 0.01 centimeters. So, this is the least count. Let us represent the least count as LC. Now, what else do we have in hand? You can see from the figure below that this vernier calipers has been used to calculate the diameter of a solid sphere. That is, a solid sphere is to be held between the jaws, the lower jaws in fact, of the vernier calipers. Now, whenever we have a look at the vernier scale and the main scale of the vernier calipers, we first need to know the position of the 0 in the two scales. Now, if you see here that if the 0 of the vernier scale is exactly in line with the main scale, then this suggests that the vernier calipers is free from 0 error. Now, in this case, we can see that the 0 of the vernier scale, they are corresponding to this point, the 0 of the vernier scale is slightly towards the left of the 0 of the main scale. If this is the case, then it is a case of negative 0 error. If the 0 would have been towards the right of the 0 of the main scale, then it would have corresponded to positive 0 error. So, this is a case of negative 0 error. Let us first calculate the 0 error of the instrument. So, negative 0 error. Of the instrument. How do we calculate this? Since it is the negative 0 error, we have a minus sign coming up. This is given as minus of the total number of divisions of the vernier scale, which is 10, minus the division of the vernier scale which exactly coincides with the division of the main scale. Now, if you take a note at each of these readings, you can see that the sixth reading is exactly in line with the main scale. So, this suggests that the sixth division of the vernier scale coincides with the main scale, or this value is to be taken as 6, and this comes out to be, now this factor has to be multiplied by the least count. So, we have minus 4 times the least count, which is 0.01 in centimeters. So, the negative 0 error of the instrument amounts to minus 0.04 centimeters. So, one part of the question is done. We are done with the negative 0 error of the instrument. Now, what have we been asked to find out here? If you take note, we have to find out the correct diameter of the sphere. Now, once we put the sphere in between the two jaws of the vernier calipers, we will see that we have a main scale reading and a vernier scale reading. Now, how do we note down the values of these two readings? Taking a look at the next diagram, the main scale reading. Of course, we are considering the solid sphere now. For solid sphere, main scale reading, let me represent this as MSR. Now, the main scale reading, how do we find that out? The main scale reading is the reading at which the 0 of the vernier scale corresponds to which value of the main scale. If you take note, the 0 of the vernier scale is coinciding with this particular division of the main scale. And how much is this division? Between 3 and 4 there are 10 divisions. So, this tells us that the first division is 3.1. So, that is exactly the main scale reading. Now, sometimes what happens is that you see that the value is coinciding to some value which is not in line with any particular value. At that time, which value are we to consider? So, you got to remember that whenever we are finding out the main scale reading, we actually consider the value which is just before the one that we are talking of, that is the 0 of the vernier scale. So, here the 0 of the vernier scale is almost in line, or you can see that it is just after the 3.1 reading. So, we got to take our reading as 3.1 and not 3.2. Similarly, if the 0 would have been somewhere here, even then we would have considered the left reading, not the right one. So, you got to note this. Now, main scale reading in this case is 3.1 centimeter. Now, how do we analyze the vernier scale reading? Let me represent this as VSR. Now, this method is same as that of the error. We got to note the division of the vernier scale which is exactly in line with the main scale. So, just have a look at it. You can see that just the first division itself is exactly in line with the main scale division, and no other reading is exactly in line with the main scale reading. So, this suggests that the vernier scale reading is the first division. So, we have the first division multiplied by the least count. Do not forget to multiply the factors with least count. So, this gives us a value equal to 1 times 0.01 in centimeters, that's 0.01 centimeter. Now, the observed reading of the diameter of the sphere. The observed reading is nothing but the sum of the main scale reading and the vernier scale reading. So, if you see the observed reading, it's equal to the main scale reading, that is 3.1 centimeters plus the vernier scale reading, which is 0.01 centimeters. So a total of 3.11 centimeters. This is the observed reading, but we are yet to find out the corrected reading. The corrected reading of the diameter of sphere. Now this is equal to the observed reading minus, or the difference of it, with the zero error. So we are to subtract the zero error from the observed reading. Now take note that subtracting the zero error, so whenever we have a positive error, it actually gets subtracted with the observed reading to give you the corrected reading, and whenever we have a negative error, then it actually gets added to the observed reading to give you the correct reading. So let's put the values. We have 3.11 centimeters minus zero error, which is again minus 0.04 centimeters. So a sum of the two, in fact, we have 3.11 centimeters plus 0.04 centimeters, that amounts to 3.15 centimeters. So as you can see, the option C stands as the correct option. So this was a wonderful problem involving a lot of concepts. Stay tuned with Academy. Thank you.